what is the reduced state or reduced order state observer? Reduced order state observer are it estimates, you can say, only non-measurable state variables, right? State variables. Okay. So next is, you can say that the state observer estimate the state variable using output and input. Yes. So a state observer ultimately estimating the state variable using the output and input. Hence, you can say that the state observer can be designed only if the system is completely observable, right? So in the case of you can say the controller design, if the system is completely controllable, then we have said the system is able to you are able to design the feedback controller gain K. Okay, and here, if the system, if you want to design the observer, it means you have to check the observability. You have to ensure the observability of the system. Why? Because the state variables, you are going to estimate the state variables using the output or input, right? So you can say state observer estimate the variable state variables using output and input. Hence, a state observer can be designed only if the system, if your system is completely observable. Observable. Very, very important line, right? Okay. And what is the easiest approach in order to design the complete observer? So the easiest approach, as you have seen, that if your system dynamics is represented in the form of CCF, then you controllable canonical form, then it means you feel better, you feel easier to design the controller again K. Here, let's say if the system is represented in the form of observable canonical form, if your system is represented the dynamics, or you can say the state equation in this form, it means it is easy easy to design, okay, design a state observer, as simple as that. Okay. Now, what is the concept of principle of observer design? Now we are going to discuss. Okay. So the principle of observer design, like, so let's say we have a plant, um, showing you. I'm just trying to draw that figure. And let's say we have the plant, ideal plant or actual plant, you can say that plant is given by the dynamics as dot is equals to ax plus bu and y equal to cx. So this is the plant. Okay, this is the plant output. Okay, and this is the actual plant by which you are going to estimate the system. You are going to estimate the system, and that estimator, that plant is represented as x estimator. Let's say this is the integrator, and this is the the A matrix. You know how it is represented, right? So I think there's no need to focus more in this figure. simply I will show you how this block diagram, what is the significance of this block diagram, so that you can understand it. Okay, so this is a plus, this is the minus. Okay, and then it is sent to this to the as a feedback to the system, this is, let's say, L. In the case of the controller design, we have our target is to design the K matrix, the feedback controller gain matrix. Here we have to design the observer matrix, that matrix is represented by L. Okay, so what it will give, it will give the, let's say, this is the predicted state variable differentiation, x dot predicted or estimation. In similar way, this is the x variable, state variable predicted, or the estimated state variable, or estimated derivative of the state, estimated state variable, right? This is the output. This is the output of the estimated state variable. Okay, and what it will do? It will, yeah, from at this point you are estimated all the states, right? Estimated all the states, and this is sent to the what controller. It is sent to the controller. Okay, so this is the diagram of the, you can say the state observer. So what happened here? The actual plant output is going to compared with the predicted value or the estimated value, whatever that less value, that minus values comes, that unmeasured value is sent to the, is act as an observer to send to the system, right? So this is the concept. The actual difference between the actual state and the estimated state is, independent by u value. This is the input. Okay, so input. Okay, and if the plant is a state, that is if the closed loop poles are located, let's say, on half of the explain, the error between the x minus x cap, x minus, let's say, x minus s cap. What is this? This is the those state variables, those are unmeasured. Okay, so the x minus s cap. Okay, so all the poles, if the closed loop poles are located on the left half of this plane, it means what it is just giving the some error. That predicted value, this is the estimated value of this data state. It is the actual, it is the plant desired value of this state. Let's say if it is a 0, it means the estimated value is equal to the your plant state. It means the error is 0. So if all the left, if the closed loop poles are going to locate it in the left half of its plane, it means the error between this x minus x bar is going to, your estimated value is approaching towards, the plant value, desired value, and it is approaching towards 0. I will tell you what happened here. First of all, you just write down the dynamics. Let us consider the state model. Let's say x dot is equals to ax plus bu, y equal to cx, y equal to, this is equation number 1, this is, let's say, this is equation number 2, and the estimated observer, or you can say the state equation. This is the plant model, right? This is the plant model, state model of the plant, and state equation for the observer. Observer means estimator. So what it will do? The state equation x dot cap is equals to a x cap plus b u. This is equation number 3, right? y cap is equals to, you can say simply cx, right? Cx cap, not cx cap. Okay, let's say this is equation number 4 also. This is equation number 4. So it means, what is the difference? What is the x dot cap minus x dot, sorry, x dot plant, ideal plant state derivative minus the estimated derivative of the state. It gives the ax minus of x cap, and it will lie 0 when all the poles located as left hand are possible. Y minus y cap is equal to nothing but the c x minus x cap. X minus x cap. Okay, so you can say that if the plant is stable, if the plant if the plant is stable, that is, if the closed loop poles, are located on left half of S plane, the error S plane, the error between actual state and estimated state, actual state and estimated state approaches approaches towards towards 0. It means x minus x cap to tending towards 0, right? Now, did it depend also on the speed of convergence? The speed of convergence of error, this means x minus x cap to 0. It means the speed of convergence of error to 0 value is the same as the transient response of the plant will come, right? It means if your transient response is, let's say, faster, then you are going to observe the state. It means your state observer will not perform well. Why? Because ultimate goal is to correct the transient response. It means you have to make the observer system faster than the transient response will get. Before you get the transient response, before you achieve the transient response, your all these states should be observed at the output and fed to the as in the feedback system. It means, first of all, I am writing here the speed of convergence. My board is not working very good. Of error, I don't know why, to 0 value, and that's why it is, I am delaying in the system. The same as that, the transient, in usual it will happen, transient response will occur of किसका, plant का, of the plant of the plant, remember. Okay, so to speed up the rate of convergence, the transient response of the observer, transient response, remember, it is very important line. The transient response of the plant should be lesser than the transient response of the observer. It means we have to speed up the transient response of the observer side. We have to make the transient response of the observer faster than the transient response of the plant. And then only what it means? It means if you are if you are able to make, if you are able to speed up, if you are able to converge, if you are able to get the transient response faster of observer faster than the transient response of the actual plant, it means you are able to receive all this estimated state almost instantly, and we are going to fed to the system before the transient of the actual plant. Okay, so you can say here, you can write here to speed up, to speed up rate of convergence, convergence, the transient response of observer is made faster than that of plant, that of plant, so that the controller will receive the estimated states almost instantly, almost instantly, right? Instantly. So what it mean? It mean to make the response of observer faster than the given plant, the difference between the actual plant output y and the estimated output y cap is fed through the vector. That vector is represented by L, right? We have already seen in the figure. Okay, so this is a rapidly updated estimated. It means the all concept, the conclusion of this concept is we have to design, we have to estimate the state variable L, state vector L the before you getting the actual plant transient response. Okay, so you can say that now come to the mathematics, come to the dynamics, how the dynamics will change. The state equation, the state equation for observer with feedback of error y minus y cap. Y cap is x, x dot cap equal to a x cap plus bu. You can see from the figure, you can say from the figure, you please see, your x cap becomes, this becomes ax plus bu, right, plus y minus y cap into L, right. It is transferred to the that point. So ax cap plus bu plus y minus y cap, and this x dot cap equal to nothing but the ax cap plus bu plus what is the y minus y cap. Y is cx, y cap is equals to cx cap. So you can write here lc mine into x minus x cap. Okay. So now see here. Now what happened when you calculate x dot minus of x dot cap, so it will provide you the x dot is equals to ax plus bu, nothing, ax plus bu. Okay, so you can write here simple ax plus bu minus of ax cap plus bu plus lc x minus x cap. So it will provide you, the bu will cancel because it is the independent of this one. So it will give a x minus x cap minus of lc x minus x cap. So when it will take the common a minus lc into x minus x cap, remember, x minus x cap. So your equation, your dynamics is changed to a minus lc, remember. So I am defining the new term, let ex estimated state is nothing. Estimated state means x minus x cap, the error between that. And this error, when you calculate the derivative of this error, it is nothing but the x dot minus x dot cap is equals to nothing but the a minus lc into ex, and also the y minus y cap, and also the y minus y cap equal to c into ex, right? So thus observer design consists of solving vector L, right? Now what was the next target? Your target is to design the SI minus of the characteristic equation yield by this modification, and the modification gives the characteristic equation SI minus a minus of LC equal to 0. You can say this is the characteristic equation, okay, the characteristic equation of system with observer, right? Observer. So that now it happens, it finds up to this point, okay. Next is what you have to do now. The some specification will give desired characteristic equation, you have to found based on that specification. So desired characteristic equation for the faster response, for faster, as we have discussed why faster response is needed. Faster response is obtained, okay, from the design specification, okay. That will be given design specification, right? A specification for the observer. So for the observer, the specification will is given, and that based on that, you just to draw the characteristic equation, compare them, okay. And how to will compare? First of all, because as you know that your target is the characteristic equation, the response of the observer should be the faster than the specification given characteristic equation, okay. So this the response of this equation should be faster than this, okay. It means uh, now we have to, how it is faster. So generally what we have considered, as you know, how the faster will become as the pole is shifting towards the left hand side. So we have considered that the difference between the pole location is the pole location of the different, this observer is 10 times greater than this pole location. The specification pole location से कितना ज्यादा होगा, 10 times more higher of this, okay. So generally the the observer response is to be made 10 times 10 times faster than response of closed loop pole system. Okay, closed loop pole system. It means for this observer poles, it means what is the conclusion? Conclusion is you have to fix the observer poles 10 times from the closed loop poles, right, of the system at the plant. Okay, so this is the concept. We will develop the design of full order observer method of matching coefficient in the next lecture. Till thank you.